Hello and welcome back to the series of lectures on high performance scientific computing. Today we will start discussing again the intricacies of computer architecture, especially when it comes to parallel computers. We will see how certain parallel machines are organized, and we'll take one specific example on how the hardware is organized, and you will see in later lectures how this hardware organization actually affects the parallel programming paradigms. So we have discussed this in the previous classes, that how different parallel machines are organized. One class of machines is called the shared memory processing machine, where you have multiple CPUs or CPU cores which have access to the same common memory. These machines are organized on the same motherboard, and because they have the same addressable memory space, they are sort of easier to program parallelly. They are also amenable to automatic parallelism tools from the perspective of compilers, and it can be used to run very large serial memory programs. The difficulty of realizing such machines is that because of Moore's law and other engineering challenges, they are difficult to sort of implement at the hardware level. While you can keep increasing the number of CPUs or processing cores on a single integrated microprocessor, it's very difficult to get to scales of millions of processing cores. Typically, in the market, we now see processing cores which are limited to about 512 CPU cores. In this class, we will also see the generic design of these microprocessors, and you will see how the memory access might not be uniform in time, and when you have non-uniform memory access, you will run into issues of coherency and latency. But the big advantage of using such machines is that you could take legacy serial programs and quickly parallelize them to get some reasonable amount of parallel speed up, especially if you're pressed for time. The second class of machines we talk about is distributed memory machines. In this class of machines, you have distinct computational nodes. Each computational node then has its own locally addressable memory space, and then they are connected together using some sort of a network. Usually for machines which do high performance computing, this has some sort of high speed network like InfiniBand, MirrorNet or GigaNet. They can also be connected using conventional LANs or conventional Wi-Fi, but then you will have very slow transfer speeds of data. What are the advantages of designing machines in this sense? Here, the advantage is that you can build very large machines. You are only physically limited by the amount of space that you have, the amount of electricity you have, and also the amount of cooling capacity you have, and most obviously the amount of capital that you have. They are somewhat easier to build and run. For example, it's much harder for me to design a machine which has 1024 processors in the shared memory configuration. But it is fairly simple for me to design a distributed memory machine with 1024 processors. The disadvantage of this kind of machines is that they are harder to program. Because now you have to explicitly send messages back and forth over the network, that means I have to come up with some sort of algorithm to distribute my problem across several computational nodes. That essentially means that I have to now do some sort of domain decomposition or decompose the problem into subparts. I have to explicitly communicate the different subparts to different nodes, and then as they do their computations, I have to now aggregate their results, exchange more information. So there is a problem of data locality. For example, if node 1 needs some information for its computation which does not reside in node 1. It resides in node 2 or node 3, then it has to sort of explicitly request it in sort of a communication mode to get that bit of data and then start the computation. In reality, how are these machines realized? Now, today's massively parallel processing machines are essentially distributed memory at the largest scale, and they are often shared memory at the lower scale. So typically what we do is that we tend to connect several shared memory machines in the distributed memory mode so that we have the best of both worlds. There are two similar examples which are given over here. So effectively what happens is that you have one computational node which will have several CPU cores, and several of these CPU nodes will then be connected via some sort of interconnect. So today's world's fastest supercomputer is located at the Oak Ridge National Labs in Tennessee, United States. It has a peak performance of about 1.7 exaflops, that is 1.7 into 10 raised to 18 floating point operations per second. It consumes about 23 megawatts of power and is made up of about roughly 8 million cores, where the primary driver is an AMD EPYC 64-core 2 GHz processor. We shall discuss the design of this machine a little bit in depth in today's class. Another machine which is present at IIT Bombay is Spacetime 2. This machine has a peak capacity of 1 petaflop or 1 into 10 raised to 15 floating point operations per second. Being a machine of much smaller scale, obviously it consumes much less power. It consumes about 200 kilowatts of power. It's still significant compared to a usual desktop. This machine has about 43 terabytes of memory, and it is composed of 9,792 Intel processors. It also has 64 P100 NVIDIA GPUs. So now the question is, what is the fundamental difference in the architecture of GPUs and CPUs? Which we will answer now. A CPU has several very powerful arithmetic logic units, but is essentially seen as a single core. It has a very large cache, it has a lot of capability, it has a variety of several instructions, several heavy-duty instructions as well. Typically, CPUs can perform very complicated calculations by themselves without breaking them down into sub-instructions. GPUs operate on the principle of SIMD. SIMD stands for Single Instruction Multiple Data. So essentially what this means is that whereas this machine follows the von Neumann cycle architecture, where it takes single instruction but works with single data. This sort of architecture works on SI. This architecture works on SIMD. So what it means is that it takes a single instruction. It could be an addition, it could be a subtraction, or it could be something slightly more complicated, but not too complicated because these are lightweight CPUs. And this instruction is then executed parallelly in one shot on multiple data. So all of this is then executed concurrently on these multiple processing cores in a GPU. The analogy that was given earlier as well, I would like to sort of reiterate it. If our task is to distribute pizzas, let's say that our task is to distribute 10,000 pizzas, we could load it up on a single truck, a big heavy duty truck, and go door to door to deliver these 10,000 pizzas as shown in this image. think of the big truck as a CPU. We could also deliver the pizzas by distributing the 10,000 pizzas among 1,000 scooters, each scooter delivering only about 10 pizzas or doing some lightweight work. That is a more efficient way of distributing these pizzas because it's the same task which is repetitive. So it is always efficient to deliver pizzas in parallel because this is an embarrassingly parallel task, and to do it serially on a CPU would take really long time even if the truck was very powerful and is able to go at much higher speeds compared to the scooters. So this is a more efficient way of doing this task. Because of the efficiency of these GPUs, also known as accelerators, there has been a great increase in the share of systems which use these kind of accelerators for the last 15-20 years. Different manufacturers have different kinds of accelerator cards which are being manufactured and being used in these large HPC systems. The performance share of the accelerators is clearly increasing dramatically as we go into the future. So it is very important for us to know how to program these accelerators and also to understand how these accelerators actually function in real hardware. Now we will look at the design of the world's fastest supercomputer, the Frontier system. These slides about the Frontier system have been made available by the Oak Ridge National Laboratory. The Frontier system essentially is a machine which is made up of 9,408 compute nodes. This machine is manufactured by the company HPE Cray, and these 9,408 compute nodes are shared across 74 cabinets. The peak performance in double precision calculation for this machine is about 1.7 exaflops. And this has been measured using different benchmarks which have been noted, and the last measurement was done in June 2024 where it reached about 1.2 exaflops using the HPL performance benchmark. The machine mainly consists of the AMD 64-core optimized third generation EPYC CPUs. So as I mentioned earlier, this is a distributed memory machine, but at its base is a shared memory CPU core which have 64 cores per node, and there are 9,408 compute nodes. This machine also has accelerators which are essentially the AMD Instinct MI250X GPUs. All these machines and nodes are connected through a very fast interconnect called Slingshot, whose architecture also we will discuss today. The programming environments are provided by Cray and AMD. The storage on this machine is of the order of 679 petabytes and is made of the Lustre file system called Orion. Now let us look at the node design. So physically these machines are organized as blades, and each of these blades have about 2 nodes. One thing we must remember is that cooling is very important for these machines because they generate tremendous amount of heat. So these machines have direct liquid cooling. So essentially what's happening is that a liquid which is electrically inert goes to cool these chips directly and carry away the heat to another heat exchanger. As I mentioned, each node is a shared memory machine by itself and has one AMD optimized third generation EPYC CPU which has about 64 cores. Each node also is connected with 4 AMD Instinct MI250X GPUs. Each CPU has a device memory of 512 gigabytes, and there is 512 gigabytes of high bandwidth memory per node. There is also 2 times of 1.92 terabytes NVMe burst buffers to accelerate calculations. All the CPUs and the GPUs are connected using something called as an infinity fabric. And each node also has 4 network interconnect devices, NICs, each capable of 200 gigabytes per second. Let us now discuss how the structure of the AMD Instinct MI250X GPU looks like. Each MI250X GPU is essentially 2 GPUs per physical card. It is actually seen by the operating system as 2 GPUs. So in some sense, you can think of this as a shared memory GPU, right? Because on each physical compute die, there are 2 GPUs. So effectively, what it makes is that there are 4 such compute dies per compute node. That means effectively I have 8 GPUs per node. Each of them have 110 compute units, have 26.5 teraflops of double precision peak capacity of calculation. Each node has 64 gigabytes of high bandwidth memory. The memory bandwidth is 1.6 terabytes per second, so extremely fast. Each of these GPUs is associated directly with a CPU L3 cache region, and you have one network NIC card which is connected to each of these GPUs directly. So if you were to look at this node diagram, you can see that this is essentially the CPU core area, and you can see there are sets of 16, 0 through 15 here, 16 to 31, 32 to 47, and 48 to 63 over here. Each of these sets of 16 are connected to one physical GPU die, which in turn has 2 GPUs each. So you can think about it as 8 CPU cores are sort of mapped to one GPU, and you have similarly about 8 such sets of cores. So totally 64 cores, each of which are connected to the individual GPUs. Now these GPUs are connected to the network interface, each of them. So sets of 2 are connected to one NIC, another set of 2 is connected to another NIC, so on and so forth. The CPU cores are each of them connected, the whole CPU, all of the 64 CPU cores are connected to 512 GB of DDR4 RAM, which is the main memory, and that speed is transferred at about 205 gigabytes per second. We also have the NVMe SSD for storage over here, which is about 1.29 terabytes of storage. That is capable of doing 8 gigabytes per second of read, 4 gigabytes per second write, about 1.6 million read-write operations per second. Let us also see how these GPUs themselves are connected. So you have these 2 GPUs which are on one die. You have 64 GB of high memory bandwidth over here for each GPU, which is able to do 1.6 terabytes per second. And they are connected to each other with fast GPU-GPU communication. You can also have the CPU-GPU communication, which is 36 plus 36 gigabytes per second on each way. And finally, the Ethernet is 25 gigabytes per second up and 25 gigabytes per second down. So you can see the different tiers of memory speeds over here. The fastest being the GPU to GPU memory, which is at 1.6 terabytes per second. You have the infinity fabric between the 2 GPUs, which is now communicating at 50 plus 50 GB per second. The CPU to GPU communication over here, which is 36 gigabytes per second. You have the PCI to the NIC connection, which works at 50 gigabytes per second, and finally the Ethernet, which works at 25 gigabytes per second. How do you connect all this distributed memory machine? Going back to this slide, this whole unit is one SMP or shared memory processing machine. And we have several of these which are interconnected to each other. So how are they connected? They are connected using this proprietary Slingshot interconnect, which gives high speed at low latency. Each of the Slingshot switches have 64 ports, which gives 25 gigabytes of bidirectional bandwidth. So basically a Slingshot is a superset of Ethernet which is optimized for high performance computing functionality. This machine also uses what is called as the dragonfly topology. So how do we connect these different parts of the network together with each other? So this is how the network topology looks. So you have a dragonfly group where a group of endpoints are connected to the switches in some sort of all-to-all mode. So in each group, you will have an all-to-all connection. Now, for each of those group has greater than one link to some other group. So in short, in this machine, there are 74 compute groups, there are 128 nodes per compute group, 32 switches per compute group and 4 NICs per node. So if you look at the map over here, you can see that this is one group. Inside you have one node. Each node is then connected to one router. Then you have this local all-to-all sort of link within one group. And then you have the global link which goes to other nodes. And finally, this is how the entire Dragonfly connection is made. So you can see that this particular node over here is connected to this router and these are connected in an all-to-all mode, whereas this guy is now connected only to two groups. This guy is connected to the other two groups, this guy is connected to the other two groups, and this guy is connected to the other two groups. And this is how the connection is established in an all-to-all mode. What is the programming environment that is offered on this machine? So you have different sets of compilers. You have the Cray compiler, which is LLVM based. You have the Cray Fortran compiler. You have the native AMD compiler, which is also LLM based. GCC. You also have one API for DPC++. Different programming models exist simply because this is a machine which is shared memory, which is also distributed memory. So you have OpenMP, you have other advanced programming models and abstraction layers like Cocos, Raja, SYCL, OpenACC, OpenCL, and UPC++. Due to the vast nature of this material, we would be covering only the most popular abstraction layers and programming models in this course, namely OpenMP, OpenACC, CUDA, MPI, and so on and so forth. What are the use cases for such a large machine? That's an interesting question. So one of the things that this machine is used in the United States is by NASA. They would like to explore different ways of safely landing a vehicle to bring humans to Mars. Obviously, it is impossible to do in-flight testing in the marginate environment at this point of time. So all this is done using computational models where you add different sorts of physics models into this re-entry problem. And you can see the complexity of the physics over here. The other use is to look at how different mining explosives can be hauled out. So this mining explosive caught fire and caused a dramatic explosion, leaving a large crater. And the debris was launched about a quarter-mile high. How do you recreate this explosion? How do we understand this explosion? What are the physics behind this explosion? This is a very, very complicated calculation. So this machine was used for doing something of this sort. So if you pack the different explosives, how does the energy sort of propagate? A few facts about this machine. We know that one exaflop is 10 raised to 18 calculations per second. So in Frontier can do in 1 second what would take about 4 years if everyone on Earth did one calculation per second. Let's say that you and I can do one addition or one subtraction per second, if every human being on the planet does this calculation, it would take us 4 years to do what Frontier can do in just 1 second. This machine has a theoretical peak capability of going up to 2 exaflops, but it has not yet been harnessed. This machine has 74 cabinets, each of it weighing about 4,000 kgs or 8,000 pounds. Each cabinet has 10% more performance than the previous machine, Titan, which used to be a really fast machine. It also uses only a fraction of power what the previous machine used. The amount of storage in this machine is about 700 petabytes. That's incredibly large. So if you were to imagine storing data on DVDs and stacking them up to reach the height of Mount Everest, we would need 25 Mount Everests to store this data. All right, thank you.